So the way to think of this is it's a two-phase partitioning. And this is the standard way we do this. So the world is built of water and particles. And there's a certain concentration here in the water, and there's a certain concentration. This notation is all over the place, various units here, milligrams per kilogram. This is the phase. Units here, milligrams per liter. Got it? It's a two-phase equilibration. And the partitioning model says that the concentration on the particles is some partition coefficient times the dissolved concentration. That's the model. That's called linear partitioning. That's what happens with Henry's laws. If I look at a gas phase and a liquid phase, and I ask myself, what's the concentration in the gas phase over the concentration in the liquid phase? It's milligrams in the gas phase, liter, divided by milligrams per liter of water. That ratio is the Henry's constant. Same idea. Okay? And this is the simplest, and in many ways, it's quite useful in some cases. Unfortunately, phosphorus and iron partitioning isn't quite this simple. And Kp is called the partition coefficient, has units liters per kilogram. In the notation of the slides I'm going to show you, we called that pi. We shouldn't have, but we did. And I didn't have a Greek symbol to put a pi in there, so. So that's how the model distinguishes what's dissolved and what's particulate, and that pi is a parameter. You have to set that. You have to tell it how strongly things partition. The other piece that's in the model is bioturbation. Before, the only mass transfer we had between the water column, the aerobic and the anaerobic layer, was diffusion. But it turned out, you'll see why in a minute, we had to add particle mixing. When I first built the model, Mike Kemp was very patient with me and would tell me on occasion things of biological importance, which I then chose to ignore. And that went on for, maybe a year at least, until finally the model I built for phosphorus flux refused to work. It just flat out didn't work. And I finally realized that I had to get some transfer between the aerobic layer and the anaerobic layer, and I'll tell you why in a minute when we talk about phosphorus. So the way I tend to build models based on the experience I had when I was young, that I had everything in the model and could never work, now I put almost nothing in the model and then try and build it up only if I have to absolutely put it in there, even if Kemp is telling me I have to put it in there. You know, he was very nice about it. He never really, was nasty about it. But eventually it became clear that I had to deal with it. And that's called bioturbation, and so now we have to worry about how much that is. Okay, well, if you read the literature on sediments, this is Bob Aller at Stony Brook did some very important early work on sediment fluxes. Here's a little diagram that he has in one of his papers of what lives in sediments, and you see you have worms, clams, and all these guys, and they're stirring the hell out of it. Well, I mean, that picture wasn't terribly convincing, but what really convinced me was this. There was a time when sediments were photographed with X-rays. Remember people taking X-rays? What was the guy's name who did X-ray photographs of sediments?
Bob Diaz.
Diaz, right, yeah. He had a camera. He'd push it into the sediment, and then they'd take a picture of an X-ray, right? It was an X-ray. Was it just a flash?
Or something, or a flash.
Yeah, and look. You see what it looks like? I mean, it's very convincing. So that didn't convince me either. I said, oh, terrific, so they're worms. But this convinced me. This was Cochrane at Stony Brook. As you may or may not know, seawater is a dilute solution of rocks. And as a consequence, everything that's in rocks is in the ocean, including uranium. And as uranium goes through its decay sequence, one of the intermediates is thorium-234, which has a very short decay life, perhaps a month or so. So any thorium that you see in a sediment has been put down there within a month or two. So if you go out in the summer and you measure the vertical distribution of thorium, by God, you see it down to 5 centimeters. And the only way it could have gotten there was if the mixing was rapid enough to put it down there, because the half-life is short. That convinced me. There's no way of explaining. Thorium is a very strong particle absorptor, by the way. It doesn't come via the pore waters. It attacks the particles. Partition coefficients 10 to the 4, so it's all on the particles. And interesting, so Cochrane had this wonderful paper where he showed in the winter, when the organisms aren't doing much, the thorium hardly gets down there. And in the summer, when they're active, it gets penetrated much more. Brilliant. That convinced me. Okay, needed worms. Hard to swallow, but
I don't think you wrote that up in the book, though.
I left that out. That's why you have me here. I tell you the stories behind what went on. So there are two things that are new. One, I've got to deal with partitioning because these substances attach to particles. And secondly, since they attach to particles, I got to worry about how the particles mix because that'll move stuff around and affect reactions. So there's partitioning in the water column, in the aerobic layer, there's partitioning in the anaerobic layer, and there's particle mixing. Everything else is the same as before. So here's a summary of how the model is built. There is, for ammonia, particulate organic nitrogen forms, it's converted to ammonia via the diagenesis reaction. The reaction is either nitrification or it escapes. Ammonia partitions, by the way, partition coefficient is 1. It's about as much ammonia on the solids as there is in the pore water. It's not enough to worry about. Nitrate is simply denitrified to nitrogen gas. Phosphorus, particulate organic phosphorus, gets turned into phosphate, and the phosphate partitions between the dissolved phosphate and the particulate inorganic phosphorus. Carl mentioned that. I'll tell you about the partitioning in a minute. Sulfate is important because once you've used up the oxygen in the aerobic layer and once you've used up the nitrate, the next electron acceptor that's available for diagenesis, decomposition of organic matter, is sulfate. And what happens is that sulfate then is the electron acceptor. It gets reduced to hydrogen sulfide, and that can precipitate as iron sulfide. That turns out to be critical, as you'll see. There is something very odd about SODs and ammonia fluxes that we noticed early and really didn't understand very well. And you'll see why that's critical. Got it? So, these two we understand. I have to take you through phosphorus, and then I have to take you through all of the reactions that affect SOD. And they are these, all of the oxygen consumption reactions. Oxygen is consumed by nitrification. Oxygen is consumed by the oxidation of hydrogen sulfide. Oxidation is consumed by the oxidation of ferrics. This is called Mackinac. Minerals are named where they were found first. So the Straits of Mackinac. This is Mackinac. Pyrite is fool's gold. That's FeS2. That doesn't oxidize very rapidly. So this is, and by the way, so how do I get the surface mass transfer coefficient? If I have the reaction rate, if I have the rate at which oxygen is consumed, I know the SOD. If I know how much oxygen is being chewed up by all the intermediates, I know what the flux of oxygen has to be to balance it. Therefore, I know the SOD. Therefore, I know the surface mass transfer coefficient. Those things are nonlinearly linked, so the model does an iteration to get it right. Finally, the transport mechanisms I need, surface mass transfer. If I know the SOD, I know the overlying water of that. The particle mixing, we've got a model that I may take you through, I may not. It's trying to calculate how benthos would affect particle mixing. So it's a function of the food, which we take to be the G1 carbon in the sediment. It's a function of oxygen. If there isn't any oxygen in the overlying water, the worms die, and there's a temperature effect. And then the diffusion is a function of the 20-degree. Since the diffusion coefficient is built into the reaction rates, there's a temperature correction on that. So that's about it. That's how it's put together. So phosphorus flux. 1941, 1942, Clifford Mortimer. Remember the Battle of Britain? 1939, London gets flattened. Clifford Mortimer is sitting in Lake Windermere in an ecological research station doing a set of experiments on phosphorus, on fluxes out of aquaria. And I remember sitting with Clifford once at a meeting. I said to him, hey, how come you weren't out there fighting, and the Germans or flying an airplane or whatnot? He said, well, he knew he was going to be drafted, and he had started up these experiments. By the way, the papers he wrote each are 50 pages long. It's 100 pages of details like you can't believe of these experiments. He just had reservoir aquaria. He laid in some sediment, put some water. He had 2 of them. One he sealed with wax, one he left open. That was it. And he watched it for, year and a half. I said to him, how come, and where'd you get the time to write all this? He said, well, I was going to go into the war, and I was sure I was going to die, so I thought I'd write down everything I know. And that's these 2 famous papers. So here's the data. I'll explain this in a minute. This is the overlying water concentrations. This is the aerobic layer. This is the reservoir where there wasn't wax on top, and so you see the oxygen stayed constant, the pH goes down a little bit. This is the generation of volatile organics, acids in the diagenesis. Carbon dioxide isn't changing much. In the anaerobic layer, you see the oxygen heads to 0. And then there's a little blip there. You see a little P in the Q? He reports that the wax developed a crack, and he had to seal it again. Wonderful. So the oxygen goes to 0. pH goes down and then starts going up. But the ammonia flux, the carbon dioxide is increasing dramatically. So there's obviously mineralization going on, and it's being trapped. It's not going into the atmosphere. Also, there's alkalinity is going up, so they're making bicarbonate as well. Conductivity is going up. So there's quite a remarkable change between the aerobic reservoir and the anaerobic reservoir. Very simple experiment. Oh, by the way, this is redox potential, if you know what that is. It's a measure of the intensity of the redox condition. So as it gets more and more negative, it's getting more and more reducing. So you see how you see this, and it's measured with a platinum electrode at these various depths. You see the depths in the sediment? And so there's the little blip of oxygen when right there where the wax cracked, and then it got back again. Don't worry too much about that. It's what's going on. The most important thing, though, the critical thing, is the observation of what phosphorus did. In the aerobic layer, nothing happened. Phosphate stayed constant. Silica stayed constant. In the anaerobic layer, phosphorus increased. Here's that little crack in the wax, and then all of a sudden, bang! Phosphorus flux just explodes out of this thing. And what he noticed was that iron suddenly jumped up. So he sees iron being generated when the system hits anaerobic. When nitrate is, where the hell is it? I don't know if he measured nitrate. He should have. But anyway, what happens is when nitrate is exhausted, the next electron acceptor is iron. And the aerobic iron which is a solid, gets dissolved to iron. So ferric iron gets reduced to ferrous iron. And you see at the same time the ferrous iron, the phosphate jumps. That's the iron. So his idea was that the phosphorus flux was tied to the iron. And the idea was this, that in the aerobic layer, there is a lot of iron. This is the formula for goethite, it's called. It's actually iron hydroxide with the water missing. So the phosphate anion sorbs to the iron oxide, goethite, by a partition coefficient to form solid phosphate. And in the anaerobic layer, there's also a partition coefficient. There's a lot less of this stuff. As a consequence, this number is a good deal smaller. And what's important to realize is that as the aerobic layer shrinks, less and less of the phosphorus is bound to the solids, but it's still in a solid phase. So Mortimer's idea was this. All of the phosphorus that's being generated by diagenesis diffuses up into the aerobic layer, is bound to the iron, and stays there. Bang. And the only time you see phosphate coming out of this thing is when the iron gets reduced, basically dissolves, or when the aerobic layer gets so small that there isn't much of it there. The iron popping out is the reduction of oxic iron ferric oxides to ferrous oxides, which are soluble pretty much. So that was the common understanding, but let's think about that. Suppose I do an experiment where I let it go on for a long time and I have a huge amount of organic matter. So phosphorus flux is continuously being generated. I'm sorbing onto iron. Eventually I run out of iron, right? If I don't have an infinite amount of iron, eventually there's no more iron, and now the material that's diffusing up into the aerobic layer cannot sorb anymore because there isn't any more iron, and therefore it diffuses out. So the Mortimer trapping mechanism works as long as you don't build a huge amount of phosphorus in the aerobic layer, because then you saturate the sorption. Do you see that? I have a finite amount of iron. I keep adding phosphorus to the iron until eventually there isn't any more ability to sorb things. It's about 4 moles per mole of 4 moles of iron, 1 mole of phosphorus per mole for 4 moles of iron is the capacity. Once I get past that, that's it. So what the heck is going on? Why is it that this stuff is continuously trapped? And the reason is that particle mixing drives down the highly sorbed phosphorus-rich solids back into the anaerobic layer. And that's what traps things. So you've got the whole 10 centimeters of sorption operating, not just the tiny little bit. And that's how the Mortimer mechanism works. And the reason I had to build bioturbation into the model was because without that, what I just described to you happens. Eventually, all the phosphorus just comes pouring out. And by the way, so I won't tell you that other story. So that's the key. The key to how trapping works is via particle mixing. Without that, turn it off and watch what happens. All of it just comes out diagenetically. You only got 2 places to put it, right? You can either flux it out or you bury it. Well, if you got particle mixing, you can bury it. But if you don't have particle mixing, you can't bury it because it isn't on the particles. It's mostly in the water and it just fluxes out. Clear? So the key thing is there's only 2 places stuff can go. You either get it back as a flux or you bury it. The reason you get an explosive release is this thing goes to 0. You have very little sorption. All of the diagenetic flux comes out, as well as all of the material, the high concentrations here, which suddenly then can communicate with the overlying water. So that's how explosive phosphorus flux works. I won't show you this. And I won't show you that. And well, it's getting late. You don't do silica anymore? No silica. Oxygen. This is the most complicated piece of the model because there are 2 things that can oxidize, 2 major components in the sediment that can oxidize to make the demand oxygen. There is the aerobic respiration of organic matter in the aerobic layer, but the aerobic layer is so small that it doesn't amount to anything. But what can happen is in the anaerobic layer, remember this is 10 centimeters, this is a millimeter, so everything, the mass is all here. So what happens is that once you've run out of nitrate and ammonia, the only electron acceptor that's there is sulfate.